Hello everyone. In this video, we're going to be integrating w of x divided by x dx. What is w of x? You hopefully are familiar with this function because we've done quite a few videos on that, but w here is Lambert's w function. I'm going to go ahead and define what it is, or at least give you an equation that you can pretty much use, and then we'll see how we can integrate this. We've done the integration of Lambert's w function before, but this time it is Lambert's w divided by x that we are going to integrate. And we're also going to be checking something at the end. Okay, let's get started, and let's start with something that, pretty much defines Lambert's w function. So Lambert's w function is basically the inverse function for something like x e to the x. So suppose we define f of x as x times e to the x, and its inverse would basically be Lambert's w function. In other words, if you switch these to like the input and output, Lambert's w function will take something like x e to the x e to the x, and then it'll return x itself. Make sense? Okay. Or if it takes anything like t e to the t, it'll return t. But one thing to keep in mind, you don't always have a unique answer. That's why we need to talk about, we're not going to talk about them, but there's actually different intervals on which this function is a bijection, and obviously there are multiple branches, including some complex numbers. So let's go ahead and see how we can integrate functions like this. In another video, we could probably do the product of x and w of x, but let's go ahead and see how we can handle this one. So again, we're going to be integrating w of x divided by x dx. I'm going to start by using substitution. A lot of times with these problems, we must use substitution because we have really cool formulas, right? That kind of gives us the relationship between x and x e to the x. So let's go ahead and call this u. So Lambert's w, or w of x equals u, and this implies, as you know, think about the input in this case. What can I input to get u at the end? From here you're going to get x equals u e to the u. That's the definition, right? If you input that as x, you're going to get u at the end. Okay, under certain conditions, of course. So that's my x. By replacing w of x with u, I got the x. Now next step would be finding dx. Dx is basically the derivative. Here we have the product rule, the derivative of u, which is 1 times e to the u, plus the derivative of e to the u, which is e to the u, times the first function, which is u. By the way, here we don't treat u as a function of x because we differentiate with respect to u, which is more made clear by the multiplication by du. Make sense? Okay, great. So if you basically we're differentiating the x with respect to, or dx over the u, you would get the expression inside the parentheses. Make sense? Let's go ahead and do all the replacements. We're going to replace w of x with u. We're going to replace x with u e to the u. And then we already have something that cancels out. And dx would be this times du. But let's go ahead and factor out a e to the u. That's going to give us 1 plus u du. Now, a lot of things are going to cancel out here. Notice that we can get rid of the u, we can get rid of the e to the u. We're going to have a 1 left here. So multiply by 1 plus u, that is just going to be the integral of 1 plus u du, which is fairly simple, right? So what do you get if you integrate 1? Think about it. Du says our independent variable is u in this case. So if you had dx, you would just use or integrate with respect to x. Same thing. Now, the derivative of which function can be 1? And if you said u, you're right, because the derivative of u with respect to u is 1. Makes sense, right? I mean, du over du, what else can it be? So they cancel out and you get 1. Some people say this is not a fraction, but it's kind of like a fraction. Anyways, the integral of 1 is u, and then to integrate u, you need to use power rule, and the power rule says you're going to add 1 to the power and divide by the power. Easy, right? U squared divided by 2. And of course, there's always that famous or infamous constant c at the end. Great. So we integrate about what is u. What are you? Who are you? Well, we know that u is equal to w of x. Let's go ahead and back substitute. So this is going to give us w of x over x dx integrated will become w of x, which is u from here, plus w of x squared divided by 2 plus a constant. Interesting. Now what do we do with this, right? We can go ahead and check our work. But how do we check? How do we differentiate w of x? That's going to be a very important question, right? Let's go ahead and check it out. So to be able to differentiate w of x, we're going to use our universal identities. What are they? So if u times e to the u is equal to x, let's just suppose, right? This basically means that w of x is equal to u, right? If you apply w on both sides, you're going to get u from the left-hand side. And now here's something interesting. A lot of times in math, you just change something and then you go back and use it again. That gives you another identity, which is sometimes very helpful. So if you go ahead and replace the u here and here with w of x, you're going to get the following identity: w of x times e to the w of x equals x. This is really cool because it allows you to take a product with Lambert's w and turn it into something simple as x. Great. Now this is going to help us differentiate w of x. How? Well, we can differentiate both sides with respect to x, and that's going to give us the following. From the product rule, we're going to integrate w of x, which is the derivative of w, times the second function. Remember the product rule. And plus the derivative of the second function. Now you have to be careful. The derivative of the second function is e to the power w of x times w prime, right? Because it's the chain rule. Remember, a function is e to the u times the derivative of that function times the first function, which is w of x in this case, right? Chain rule. And then this is equal to 1. Why? Because the derivative of x with respect to x is 1. Easy. Now let's go ahead and factor out some numbers. We can factor out w of x times e to the power w of x. W prime times e to the w. If we factor that out, we're going to get 1 plus. Notice that this is going to go out and this is going to go out. We're going to have plus w, 1 plus w inside. Now, our goal is to solve for w prime. So don't leave this on the left hand side. Divide by this. Here's what we're going to divide both sides by, and that's going to give us w prime. So w prime, in other words, is going to be 1 over e to the wx multiplied by 1 plus w of x. So we got another formula, and there's definitely more than one way to express it because we have the identity wx times e to the wx equals x. So at any point you can replace this with x over w of x and vice versa, so we can get different identities. But we're not done yet because we still have to check our work, right? So what are we checking? Well, this was the integral, right? Is this an antiderivative, right? Without the c, you can, I guess, call it an antiderivative or general antiderivative. Now if you differentiate both sides according to the results, we should be getting this, right? But I'm going to put a question mark because we don't yet know if this is going to work. Let's go ahead and differentiate both sides. The derivative of w plus, this is kind of like chain rule again. You're going to bring the 2 to the front, reduce the power, and then divide by 2, but also multiply by the derivative of the inside, which is the chain rule again, and the derivative of c is 0. That's why we put a constant there. 2's cancel out, and we end up with something like this. W of x plus w times, w prime I meant. W prime plus w times w, is this equal to this? It's kind of like hard to obtain, right? Let's see what we can do. We can actually take out w prime, and this is going to give us 1 plus w. And now this is time to use the derivative. What was the derivative of Lambert w? This one. Let's go ahead and use this. Replace Lambert's w, or w prime, with 1 over e to the power wx times 1 plus wx multiplied by 1 plus wx. And that's going to give you, tada, these two are going to cancel out, and 1 over e to the power wx. Wait a minute. Aren't we supposed to get wx over x? Yes, but think about it. When you have wx times e to the wx being equal to x, you can now replace this with x over wx, and its reciprocal is going to be w of x divided by x, which verifies the original function. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.